So now we have,
Well, I mean, if I was building it looked like severe.
Oh, maybe, yeah.
so 20 centimeters, and you have a,
Actually, I have a exam problem that's very similar to this, if we just wanna do that one.
Okay,
'Cause I was
please.
that's why I didn't know. And this is all theoretical too, so it'll just work out the equation for us. Fieldwork processing plant has a very long pipe with radius R. I don't wanna draw your pipe, please. Radius R filled with contaminated water. The water has an activity of SV becquerels per centimeter cubed.
SV in units of
Becquerels per centimeter cubed.
becquerels per centimeters.
Photon energy E is emitted with frequency F by the contaminant. Derive an expression for uncollided water. Oh, that's uncollided. But we can do collided and uncollided. Water Kerma rate at the pipe's axis.
At the pipe's axis?
You're gonna have to do a geometric transformation for this one.
This was not gonna be very happy.
Well, can we do the uncollided first and see if we can collide? The uncollided one is actually a test one.
Yeah,
I was curious.
okay. So let's take a small unit of volume here. And let's imagine that this is this would be our transformation. We're gonna imagine that we have a plate here that extends from 0 to infinity of contaminating or radioactive material. Okay? We'll get the dose from this plate at point P. We'll multiply it by 2 pi, so swing this around and then multiply it by 2 to flip it up on the other side. Sound okay?
Yeah.
A little bit better than this one.
Yeah, no, that's what I was gonna suggest, so that, yeah.
Alright, so this is not gonna be
Do we have any kernels for area sources?
it might have to be line source.
Yeah, we might have.
Bunches of line sources.
Yeah.
And then you have to still find it from that point. You have to find the dose at that point.
That's okay. So let's say for a line source right here, well, let's just give it SL. I don't know what SL is, but it's gonna be something. This is R out to here. So let's say from this chunk right here, our differential dose is gonna be, is it, I guess we're gonna have, okay. It's gonna be SL dx over, R squared plus X squared, where this is X, times 4 pi, times e to the negative R squared plus X squared mu. Okay, so we'll have to integrate that across from 0 to infinity to get the dose at this line. So the dose for this whole plate is going to be this integrated over from 0 to R.
What's the argument of the exponential e to the minus?
R squared plus X squared.
Okay, that's what I thought.
It's GR. probably have to numerically integrate, you could do it,
Yeah, you didn't have to get any steeper rules some sort of.
yeah, it's not friendly, but you could get it.
I think this is well, once we multiply this by two pi and, well, by 4 pi, well, the 4 pi's would just cancel out.
Yeah, so our dose is gonna be, we're gonna rotate this around two pi, or if you say you wanna integrate this around this whole circle, you're gonna multiply it by two pi, and then to flip this up to the other side of the pipe, you multiply it by two times both these integrals from 0 to, let's call this capital R, and 0 to infinity of this stuff. Okay? So I guess your final answer would be D is equal to, and yes, the 4 pi would come out, go from 0 to R, 0 to infinity, response function, line strength, dx, dr, e to the negative, r squared plus x squared, mu, over x squared plus r squared. And this line source is not, that's not what you want in the final answer. So you have to find what
SB
that-
all the SB.
Yeah. So, whenever you, so let's take a loop of this, let's spin it around. So, we'll have a hoop of dr with thickness dx, spun around, that has a length of 2 pi r. So the volume of this small differential hoop around this will be, the volume of this will be 2 pi r dr dx. Okay? So the volume of, and that's going to have some source volume. So, is there a way you can convert that? Yeah.
What's 2 pi r dr dx?
That's the volume of,
Is what?
that's the volume of a ring of dr and dx around this way.
Why don't you just divide SB by the surface area of, or not the surface area, the cross-sectional area?
Maybe.
SB is volume divided by the
So-
area, and you get the length here.
Source volume divided by, we divided by 2 pi r dr. How about that? Because, yeah. So that would leave out dx. This would be SL. So
I don't think it's dr, I just think it's just SB over 2 pi r.
SV over 2 pi r.
Yeah, because if you have the dr in there, then your integral doesn't work.
Well, this will only give you, this will give you units of area.
Pi r squared, not 2 pi r. You get what I'm saying? I don't know if this is right.
Yeah. Maybe.
Like you have a volume.
Right.
It's one.
So this, yeah, you can do that, but this is the way you can do it if you wanted to actually go solve it out. If you just wanted to say that, hey, we can do this integration, just say that the dose is equal to, let's use this, actually no. So let's say that you just have some piece of volume here that is,
We can make it as cylindrical shells and integrate from 0 to r.
yeah, you can do that.
And the cylindrical shell will transform it to line, and SV will be obtained from DSL by SV over the cross section area of the cylindrical shell.
Yeah. You could do that. I wonder if you could just say that you just want to integrate from 0 to infinity, integrate across 0 to r, and integrate across 0 to 2 pi, and multiply by 2 times whatever dose you get from a volume inside there.
Brian,
Yeah.
you guys might have been saying this, I've just been kind of reading and not listening, but on page 171, if you have a cylindrical volume source, like with an attenuating medium such as water, you can use, did they want D0, Michael, or D total?
Yeah.
Okay, so D0 is equal to SV times response function over 2 times the integrals over your radial distance and your height.
Okay.
And so you could set your height to be infinity and then multiply that by 2.
Yeah,
zero to
yeah,
infinity.
no. That's good. So, I'm not sure if this is the same thing, it might be.
6.62, yeah. You could just write equation 6.62 for this solution.
Yep.
Yeah, you could. I mean, it's
So,
exactly mathematically.
you would do this, but you would multiply it by 2.
Right, because you have 2
Because
of them.
because this, yeah, just look at page 6, or 177, 171.
Yeah, so you just can write 60.
What? Have the solution.
Yeah. Yeah, it's pretty much the exact same problem.
But, and you're right, it isn't happy because the solution of it relies on the G functions, which are functions of the E functions that you showed us.
Yeah, I don't even want to think about that.
Yeah.
Or function by function.
So, where H would be infinity.
I wonder if you would accept equation 6.64.
So,
You might
lesson learned,
read the book.
don't jump into a problem right away, kinda maybe see if there's an easier solution in the book.
I think this method would get us the right answer, it's just.
Yeah, I don't know how you find SL,
Right.
so.
I would just write